Hello, in my last video you might remember me saying that BVH is the only thing missing for my engine rewrite that really is going to have an effect on things, and it is finally here. It saves us around 200 microseconds on the CPU, it saved around 100 microseconds on the RDP, so it is pretty good. Now you might wonder, what is a BVH? Well, so in Mario 64 there is a grid of collision cells. So this whole map is divided into a 64 by 64 grid, 4096 cells in total. Which, first of all, that takes a lot of memory to store properly, but also it is not that great. So let's say I'm right here. The game picks one 4096 other volume, like a chunk out of the sky that is projected all the way to the bottom, and it stores all the collision triangles that I could ever touch in there. So in this chunk I'm in right now, it's probably going to be like the mushroom, and like this part of the mushroom, this part of the mushroom. It's going to be the triangles here, it's going to be this part of the mushroom. So there's still going to be like, what, 30 triangles in there maybe? So it is not that great. Now a BVH works differently. A BVH is like a tree of volumes. Look at this image here. So we start with one volume that encapsulates everything. And then inside this volume, there's two other volumes. One volume right here that contains these 5 triangles, and then one right here that contains these 2. And then inside the one that contains 5 triangles, there's another 2 volume, one with 2 triangles and one with 3. This is just an example. So that way, all you have to do is you have to check which volume you intersect. So right now, maybe if we stand here, we check, hey, we intersect this volume, we intersect this volume. So we only need to check these 2 triangles. Basically, you have to think about a bunch of tiny volumes that we're intersecting. This is also kind of showcasing it in 3D. Let me find a better picture. This one, this is kind of showcasing it. Yeah, this has the tree structure too. See right here how there's a big box A, and then there's a smaller box B. So we could go into B if we intersect B, and then smaller box C, right? So we only have to do box intersections, which for one are much cheaper, but also this new data structure is very small to store, which means we need to iterate less data. And I have made it so that we never have to iterate more than like 8 triangles in one thing. It usually ends up being just like 2 or 3 triangles, but 8 is the absolute maximum, which means we only have to iterate a quarter of the triangles at most, at the very most. Or look at something like this, dude. This is gonna be hella collision triangles in the vanilla Mario, but not in ours. So I'm very happy with this. This actually did a lot more optimization than I thought it would. It saved a lot more RAM than I thought it would. I expected this to do absolutely nothing, so a positive surprise. But also, this means it gets us further away from the Super Mario 64 source code, which is good. I want this to be 100% custom code. And this was one of those codes that was a thorn in my eyes. The code for this is very simple to implement, like it's literally just this. I just do one intersection test. If it fails or misses, we just keep going. We have, actually, this image is a bit misleading. This is not what we do. Let me show you how I iterate this. So let's say this is our tree. We actually go like here, 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 and then if we fail this, we don't go back up and then down. That's nonsense. We just go here right away. And then if it fails this, we just go here right away. We don't go here, here, here. So it saves a little bit of data throughput. It stops us from having to go down and up on the stack. Saves a lot of memory. It's pretty good. That's it. Bye bye.